All right. So Ryan is a professor, assistant professor of computer science here at Harvard, the School of Engineering and Applied Sciences. His interest is understanding computation and intelligence and developing artificial systems that can discover complex structure in data. He's a data scientist by definition then. He completed his PhD in physics, University of Cambridge, and moved from one Cambridge to another Cambridge, somewhere in between.
The real Cambridge.
The real Cambridge, yes. So a little bit warmer than this.
Yeah.
So Adam will be talking about taking himself out of the loop.
Great, thanks for that introduction. I'm very happy to be here. This is a great, really fantastic event. So I'm going to tell you about machine learning today, and in a sense I'm going to be telling you about what I think of as kind of meta machine learning. So trying to really make machine learning about machines doing the learning and not about people. So first I kind of want to start out with kind of just telling you about machine learning broadly. It's a very hot topic. It's something that's receiving a lot of attention these days. And like a lot of things, it's getting, there's a lot of hype surrounding it. At some level, the hype is about the idea that machine learning is something that I can throw a big bag of totally unstructured data at, and it will give me interesting answers and tell me everything I want to know. Of course, the reality is that it's both sort of less glamorous and more foundational, which is that machine learning fundamentally, I think, is about the interface between statistics and computer science. It's about taking probabilistic ideas and about reasoning about noise and data and structure and applying algorithmic thinking to those kinds of ideas. Obviously, it's heavily motivated by AI, and this is kind of the area that it comes from, but these days it does a lot more than just think about sort of artificial intelligence, but it's broadly about finding statistical structure in data. And more generally, the way I think about what machine learning is about is a kind of new way of doing programming. So the traditional way that we think about building programs is we think hard about how we might want to map inputs to outputs, and we sit down and then write a program that executes that. Okay? Machine learning is about the idea that I have inputs and maybe I have examples of outputs that I'd like to be associated with those, and I try to automatically generate a program that can produce those outputs given those inputs. So it's about taking examples and going from those to a program. And necessarily that's about finding, in a sense, statistical structure about the association, the joint probability between inputs and outputs, and also feeding in assumptions about the structure of the world that makes this possible. So hype aside, this is something that's been extremely successful in the last couple of decades. And in fact, you sort of interact with machine learning algorithms and the results of machine learning in many different situations sort of every day, from something like speech recognition in your iPhone if you use Siri, to the kind of suggestions you might get from Netflix for what movie you might want to watch, to different kinds of new innovations in developing personalized therapies, to say nothing of the neat stuff that Cynthia was talking about. Machine translation, like we just heard about, and then also exciting new developments such as predicting the properties of biomolecules for drug discovery, and just everyday things like in your camera and your phone doing face detection to automatically identify and focus on the people, say, in an image. Okay. Within my group and here at Harvard, there's been really exciting opportunities to apply machine learning in the sciences. So just to give you a couple of examples to kind of set the stage for what the rest of what I'm going to talk about. So we've been collaborating with, for example, folks at UCLA to apply machine learning to detecting cancer in cells using a non-invasive technique called flow cytometry. One of my postdocs, Shamim Namadi, has been working with collaborators at MIT and local hospitals to develop machine learning techniques for processing physiological signals and predicting ICU outcomes. Luke Bourne will be talking later this afternoon from the statistics department here about work he's been doing with one of my students, Ann D. Miller, who's sitting up here somewhere, about modeling professional basketball, which is super fun. Alanis Buruguzik in the chemistry department, he and I have been working together on machine learning models for predicting different kinds of the properties of sort of new of sort of novel organic molecules. I think there's a couple of students involved in that project in the audience here. Bob Data at the medical school, we've been working together to come up with quantitative models for mouse behavior using machine learning to enable us to discover the sort of underlying genetic and neural correlates of behavior. And also, I've been collaborating with folks at Berkeley and Berkeley National Labs to develop new models for essentially the universe to understand the structure of the early universe. So there's a lot of different ways that we use machine learning and interface with the sciences. But there's kind of a problem here, though, as I tell you about these kind of projects, which is that the promise of the idea of machine learning is that it should in some sense be automatic. And so none of these people should need me, right? The idea is that we should be developing tools and developing methodologies that enable smart scientists to be able to solve their own problems. Now, I mean, Luke is a statistician. He really doesn't need me. But the rest of the people here, I contribute something methodologically, when the whole idea is that I should be developing tools that get used broadly, sort of without me in the loop. And so I view this as a kind of big lie about machine learning, right? The idea is that what's happened as we've gotten better at machine learning is that it's become possible for experts to get good at solving harder and harder problems. That is, experts in machine learning methodology to get better at solving problems. What we really haven't achieved, and something that I think is absolutely crucial, is developing better tools for non-experts. That is, for domain experts to get better at solving their problems without having to become also an expert in machine learning. And this is something that I think we sort of really need to achieve. And let me just give you a couple of examples of successes where experts have done amazing jobs solving difficult problems, but that it's been very difficult to translate those successes into sort of broader, the broader field. So a really good and kind of current example is the idea of deep learning. And I'm sure a bunch of you have heard about deep learning. It's been in the New York Times. It's a really big deal, and it's essentially a rebranding of neural networks. And that's not a negative thing. Neural networks are a great idea, and faster computers and more data and new insights have led to us being able to train them to solve difficult new problems. Okay, and this has resulted in kind of interesting big investments by companies like Google and Facebook and Microsoft. But kind of the problem is that it requires one of essentially Jeff Hinton's grad students in order to implement this stuff for you. That if you wanted to just start applying deep learning to some problem you're interested in your company or your lab, then it's not hopeless, but it's close to hopeless. And this is because there's just a ton of decisions to make, and it's kind of a dark art to figure out how to do it. And indeed, the way Google and Facebook have done this is not by trying to train their internal engineers, but by paying whatever it takes to hire the best people from academia to come and work for them. Rather, that is to say, hire the experts rather than sort of commit to internal tools to solve the problems. What's that? Hire Jeff Hinton, so Google hired Jeff Hinton, and Facebook just hired Jan LeCun as examples. So these are senior people in kind of the area of deep learning, but that's not the only example from machine learning. I mean, that's kind of neural networks are kind of one corner. Then there's there's probabilistic modeling of text, so things like graphical models, in which people have developed these exciting large-scale topic models, so applying things like latent Dirichlet allocation using stochastic variational inference to big data sets. Again, great stuff, really cool, but requires somebody who's an expert in these things to realistically implement. And this is this is kind of an unfortunate state of affairs because there's a lot of people that might want to be able to deploy these kinds of ideas to to their own data and without having to sort of bring in Dave Bly or Matt Hoffman. As another example, and yet kind of another corner, so there's obviously neural networks and there's graphical models and things like that, but also there's things like support vector machines that are really, really important to the field of machine learning that people use in a lot of different contexts, but these things are hard to tune too. So we have something like, so for example, there's been interesting successes in applying these kind of latent structured support vector machines to things like protein affinity prediction. And they, again, works really well if you really know how to tune it, if you know how to set the parameters and make it all work. These are non-convex objective functions, and it's great empirical results if you're one of the authors on the paper and know how to make it work. Okay, so this is an unfortunate situation, and so it makes us ask the question of kind of whether or not it's really the machines that are doing the learning here, right? That what happens is maybe people get really good at building in inductive biases and trying to understand how to set these parameters, and that there's a sense in which humans are doing the learning for a particular kind of tool. But I think we got to get past this. I mean, part of what we want to do is build tools that allow us to weather the data storm, as it were, right? To be able to deal with this, even if you're not a dyed-in-the-wool machine learning expert. And these are kind of I view these as meta challenges. So these models are getting good, but they're getting good because they're getting more complex. And so that means a lot more parameters. And alongside those parameters are more sophisticated fitting methods. The optimization procedures, particularly when you're talking about non-convex objectives, tend to be pretty complicated, and the results you get are highly dependent on how you run that optimizer. Obviously, this is all about sort of these things not being possible really for non-experts to apply. But even within the expert community, this results in science that is not as good as it could be. And that's because the results become less reproducible. You want to be able to pick up a paper that talks about some new methodology and feel comfortable that you could reproduce those empirical results without having to know all the black magic that goes on behind the scenes. But if there's a whole bunch of details that are there that were necessary to make it work, then it's really difficult for that sort of new methodology to be considered kind of a contribution to the literature, right? Because nobody else can use it but you. And that's kind of a sad state. So the question is, how do we get around this? What do we do? And there's a couple different things you can think about for how to take people out of the loop here. One version, of course, is to let's just design algorithms that don't have many parameters. That's, of course, like, that's hard to do, right? And it's a good idea, but there's no free lunch. And there's no free lunch because machine learning ultimately is about specifying an inductive bias, putting some constraints on the world and saying we're going to try to find models and hypotheses about the world such that they're consistent with the data. And if we don't build in those assumptions, then we're not going to be able to learn anything, right? And so the idea of having these knobs to tune and setting assumptions about the world really go hand in hand. One thing we could try to do is remove these kind of parameters analytically using marginalization. So this is where you have maybe a big graphical model and you can integrate out some of the parameters and make the model effectively smaller. So for graphical models, you might be able to do this, but for things like SVMs and deep learning, there's not really a clear analog. And even in things like graphical models, it's still hard because now you're trying to do some integration that you're going to need to do probably numerically. That integrator, if you're using Markov chain Monte Carlo or something else, is itself going to have parameters, and now you're back where you were. So what I'm going to talk about today is this last thing. I'm going to talk about the idea of trying to automate the search for good hyperparameters, for setting the knobs of these things in an automated way. And it's going to use some of the methods that were just mentioned in the last talk about response surface experiments, but I'm going to call it something different. I'm going to call it Bayesian optimization. And it's going to be interesting and difficult in a different kind of way to view optimization because we're going to be dealing with objective functions that are very expensive to evaluate. And that's because we do have a way to evaluate the quality of hyperparameters in our models, right? If we have some SVM parameters or some learning rates for our neural network, we can train the neural network and then ask how it does on unseen data using cross-validation. This is something well-defined. Statisticians do this all the time. Machine learning people do this all the time. It's just really expensive to evaluate that objective function. And so people use relatively unsophisticated methods because it's so expensive. So things like grid search, if it's really low dimensional, or random search, if you sort of like don't have a lot of knowledge of the structure, or my favorite, which is grad student descent, where a grad student sits in a dark room and turns the knobs on the thing until they've got good enough results to submit the paper. And if you don't think that happens, yeah. So it's not that anybody's acting maliciously, right? It's just that, it's not the kind of science we want to be able to do. We want to make tools where it's very transparent how somebody got these parameters and how you could replicate their results. All right, so we need to automate this and make it intelligent. And I think we can do better using more sophisticated tools and kind of, in a sense, kicking the machine learning up a level and using intelligent tools for optimization. Now we have a big optimization toolbox, broadly speaking. What Bayesian optimization is about leveraging uncertainty and modeling to make great decisions when you're evaluating the objective. And the reason that's interesting here is because we don't have a lot of structural information about the objective, and it's extremely expensive. When we're in this regime where the objective functions are expensive, then rather than making kind of like simple local decisions like you might do in random search or evolutionary algorithms or something like that, you can afford to spend some effort doing some modeling and making great decisions about where to go. And we do that by essentially taking the framework of Bayesian non-parametric regression, in particular Gaussian processes, and applying it to modeling this objective function that we don't know. And the main thing is that it turns out that in kind of an information theoretic sense, we can turn the crank on these models and make great decisions about evaluating this expensive objective and finding good hyperparameters for our models that are going to trade off exploration against exploitation. That is, trading off finding possible new regimes where the parameters are really good against greedily pursuing parameters that we think are kind of, we already think are good. And the reason we like this Gaussian process framework is because it's quite general. It allows us to think not just about simple functions like like sort of RD, but allows us to also think about complicated discrete structured objects, which will come up later. The sort of basic idea is pretty simple for sort of Bayesian non-parametric regression here, and I'm not going to go into the details about Gaussian processes in this talk, but the main thing to think about here is to imagine that we have a set of points in some one-dimensional space here, and we've seen, say, 4 points in this, 4 evaluations of this function, and we can think about random functions, in a sense, in the posterior, that is, that are consistent with the data that we've seen. Okay? And we can think about lots of different possible functions that might interpolate these data. And we could add noise and handle that, but let's just talk about interpolation for now. And essentially what a GP allows us to do is reason coherently about large collections of functions that would be consistent with the stuff we've seen before. Okay? So if these are previous experiments we've run, and say we want to minimize and think about the goodness of this, then what we might try to do is make decisions that integrate out over all of these possible functions, right? So that are good, that are going to be good kind of no matter what the true underlying function is. And in the Gaussian process in particular, it turns out that even though there's an infinity of possible functions that can interpolate those points, that you can compute these predictive marginals for new points in closed form, and they have nice Gaussian distributions. It turns out just to be a little bit of linear algebra. So we can turn this kind of regression tool into an optimizer by thinking about how we would take that model and what the properties would be of a, under the model of a good new point to evaluate. So again, let's imagine that we have we're trying to minimize some function. We don't know what it is. We've seen three points evaluated from it. And there's a whole bunch of possible objectives that could be sort of the truth here. We don't have gradients. We don't know anything. We just kind of are assuming that the function is kind of well-behaved in some sense, right? So we have our current best guy here, a bunch of possible functions. What we could do is think about the probability or the expectation of how much better some new point is along the x-axis than our current best. And because everything is closed form of the Gaussian process, we can compute this really easily. And we can compute this quantity called the expected improvement, which is essentially an auxiliary function that's a property of the model and not of our really expensive function. So we can interrogate this sort of auxiliary thing as much as we want without ever having to go run our hour-long experiments or day-long experiments, right? And so then we can think about maximizing this kind of offline rapidly and then make a great decision about where to go next in our optimization, right? So let me kind of give you a little bit of a cartoon about the way this would work, where say we had the ground truth was this red dashed line, and what I'm showing you here are the mean posterior function here given these 2 observations, and the kind of uncertainty estimates around that. And along the bottom is this acquisition. So the way this is going to work is this acquisition function is big in places where there's a lot of uncertainty and where the function tends to be low in expectation. Okay, so we're trying to go for places where we don't know that much, but we kind of are optimistic that it might be good. And then that's going to maximize this function down here. So we pick that point, and we go and we run that experiment. We get that observation. And now we're sort of pinching down our uncertainty around there, which is great. And we discover that maybe that wasn't so good after all. And we repeat this process again, right? So then we go back in, and we recompute this proxy function, and we iterate this. And what will happen is we'll essentially zero in on some places for which we think we have reason to sort of think that they're quite good values globally, but we don't ever need to learn about places for which there's a lot of uncertainty, but we have a good reason to believe that they're actually quite bad values. Okay? So this is kind of a nice idea, and it's kind of satisfying from an information theory point of view, because it's sort of like looking at the expected improvement of the next step. And so the question is, and I should say this idea of sort of response surface optimization, Bayesian optimization, these ideas have been around for decades, like since the 50s at least. And yet people are still using this sort of grad student descent procedure on a lot of these things, and in a lot of other kinds of problems as well. And the question is why? Why isn't anybody using this? And I feel like there's a couple of different reasons that these methods haven't sort of been mainstream, at least within kind of machine learning. And the first is that I think they classically tend to be pretty fragile. Like if you don't have a good model, they'll tend to not do, they might tend to make sort of catastrophically bad decisions. Like a lot of things, there hasn't been just a tool that you could download and run that would solve this problem for you. And realistically, for people who do methodology, right, you don't want to have to invent, you don't want to have to write the the code yourself from scratch if you can avoid it. You'd like to just be able to get, download something and run it and have it do something sensible. And then also in a modern computing environments where we have parallel resources, this thing runs experiments sequentially, sort of in the classical setting, but we'd like to be able to run parallel experiments. And so I'm going to tell you about how we've been sort of tackling these over the last couple of years. So the first thing is thinking about the model for the function. So this Gaussian process model. Ironically, that fragility is about the fact that the Gaussian process has its own parameters, right? And so now you have to set the parameters for that thing, and it doesn't really feel like you've saved any effort, right? If you have to tune the parameters sort of at the top. But if you recall, one of the other kinds of methods that I mentioned for trying to eliminate parameters in a machine learning model is the idea of marginalizing things out. And it turns out that because of Gaussian process without having to without having to think very hard. That is, you don't have to add new parameters to make it go. And this turns out to be a pretty big win, where we're essentially doing the same kind of thing with Bayesian optimization, but now integrating out kind of global properties of the function as well. So to give you a sense of what I mean here, without going into sort of details on the guts of Gaussian processes, if we had some function, if we had some, say, 5 evaluations here, we can think about different functions that are sort of consistent with those data. Some of those might have very long length scales like this red line, and others might have much shorter length scales. And those length scales are the kind of hyperparameters I'm talking about here with the Gaussian process. But if we could integrate those out using Monte Carlo, then what we could do is make decisions under this Bayesian optimization framework that are going to make as many of these length scales happy sort of in expectation as possible. And it turns out that if you do this, you get much more robust results in this framework. It's not surprising. We don't have that much information. And when you don't have much information, marginalization under kind of a nice Bayesian model is a good way to sort of be robust in some sense. And empirically, if we look at kind of classical type machine learning problems like logistic regression for handwritten digit recognition, so here being lower is better, and we're trying to get as low as possible, as soon as possible, going left to right, then essentially using MCMC gives us an improvement over the traditional kind of empirical Bayes method. And this is the kind of thing that people have been terrified of previously, because if you know about Markov chain Monte Carlo, you think of that probably in a knee-jerk way as being like the most expensive computation in the world. And so the idea of running that in the inner loop of your optimizer seems like a terrible idea. But it turns out that if you need to run experiments that are going to take a day to run, spending 30 seconds of time to run MCMC just isn't that big of a deal, right? So you can afford to run MCMC and make a lot better decisions when you're doing your optimization. Same kind of thing, and I won't kind of go into detail here, but in general, people have tended to make quite smooth and strong assumptions about the structure of their objective functions when building these models. And in particular, they've tended to use this kind of exponentiated quadratic, squared exponential type, very, very smooth, infinitely differentiable functions. But the truth is the world is a messy and annoying place, and what we'd like to do is back away from those extremely smooth assumptions in performing our regression. I mean, these are the assumptions about our unknown objective. And it turns out that if we use this broader Matern class of functions and make weaker assumptions, such as maybe that the sample paths are only like twice differentiable, that you're not sort of asking quite so much, and yet you still get good convergence. And so here's this kind of trying to tune this structured SVM problem that I showed you earlier on protein motif finding. And the main thing to observe is that if we do the kind of classic thing where people assume extreme smoothness on the objective function, it looks like it's not even going to get us the right answer no matter how long we run it. Whereas if we make better assumptions that kind of fit the, basically weaker assumptions about what the function looks like, then we get better answers more rapidly. Okay, and sort of like hitting the tops of a few other ideas. I mean, one thing that Bayesian optimization classically has not included is a notion of cost. In real life, there's a variety of different experiments have different durations, maybe take different reagents, have different amounts of, cost different amounts of money, and we'd like to be able to account for that when performing the optimization. And so what we can do is take our Bayesian modeling framework and kind of extend it to include a function that's modeling that additional cost, and then extend things so that instead of just trying to find, say, the expected improvement, we can try to find the expected improvement, say, per unit cost. And again, because we're in this regime where things are really expensive, we can afford to do this kind of additional modeling. And so this is motivated by the idea that if you have a deadline and these experiments take different, different amounts of time, then you want to explore in a cheap way before you start maybe zeroing in an expensive way. So here's the same kind of figure I showed you before. The top is the model for the function, but now the bottom is discovering a function of cost along the way. Okay? In this case, it's discovering duration. And what we can do is cook up an acquisition function that is penalizing with cost, essentially, and doing the same kind of thing, but preferring to explore cheaper places first. It's a kind of a natural intuition. And not surprisingly, if you kind of build this model, then you get better answers faster in general, right? Because if it's something that is cost, that has no knowledge of cost, is going to not make intelligent decisions about going, and is going to go to places that tend to be slow, basically. Again, this is this kind of SVM structured protein motif finding type problem. More interesting, actually, I think it's this problem, actually, which is, so this is training a big, deep convolutional neural network on the CFAR10 data, which is a kind of benchmark for visual object recognition. And what's interesting about this is that Alex Krzyzewski is one of the 3 people who was acquired by Google. So Jeff Hinton and Alex Krzyzewski and Ilya Sutskever. And he was acquired for his expertise in convolutional neural networks. And this was his code. So his code was sort of living inside here. And what we did is expose the parameters and ran essentially the same experiments, but asking Bayesian optimization to find a better solution for the hyperparameters than Alex did, essentially, and Alex wrote the code, knew exactly how it works and everything, and it blew Alex away, right? So it actually beat the human expert who wrote the code. Okay, so this has like 12, 14 parameters, something like that, and they're kind of complicated parameters about regularization, deep in some network, and so on. And the takeaway here is that even sort of like the foremost expert in this area and the guy who wrote this code can't beat just sort of like systematic reasoning under like a relatively simple model. And this basically boils down to the fact that humans aren't good at optimizing things in more than about 3 parameters, right? So this is why people have this kind of black magic surrounding these optimizations. It's just very hard for us to reason about it. And so this is about systematizing these kinds of decisions. Sort of in the last couple minutes, I'll tell you about, I mentioned parallelization, where the idea is that we want to be able to not just run one experiment at a time, but multiple experiments at once. We might have a cluster of GPUs for training our convolutional neural network. We can take advantage, again, of the really nice closed-form properties of the Gaussian process to basically fantasize the outcomes of future experiments. So you run an experiment, it's running, it's off, and we want to start another one. We don't know what this one's going to come back with, but because we have a nice predictive model, we can just like fantasize a set of possible futures, essentially, and then try to choose another experiment that's going to make this experiment, that's basically going to be happy under the average possible future. Okay, so you can think of this as a kind of Monte Carlo estimate of possible futures. So if we have these 3 experiments, for example, that we've completed, and we have, say, 2 more experiments that are off on our cloud running, then what we can do is essentially sample possible functions that are consistent with those guys, and then make a decision that is, in a sense, sort of like, again, happy under all expected future worlds, and go ahead and start that one up. Because then kind of no matter how the other guys come back, this is still probably a pretty good decision. And it turns out that if you apply this to so if we apply this to the kind of, I mentioned this online latent Dirichlet allocation, so this is the stochastic variational text analysis, set up that even with a very modest kind of parallelism of doing sort of like 10 of these things at once, it gives us a really big gain, and that doing this fantasizing really doesn't introduce kind of an additional cost. That is, the stupidity of fantasizing doesn't sort of hurt us that badly, and we get answers quite a bit faster. Okay, so we've been doing a lot of other stuff too. I mean, this has turned out to be kind of a very exciting area for us with a lot of potential applications outside of machine learning, where once we kind of feel like we've made some progress on making these tools robust, it turns out that a lot of people have difficult optimization problems that we're hoping to be able to help with. So a couple of examples, we've been working with, so Alanis Peruguzic and I have been working with Samsung on trying to develop new materials using these kinds of ideas, plus interesting sort of theoretical chemistry. Working with folks at the Broad Institute on using this to design DNA sequences for particular protein affinities, and also with some mechanical engineers at MIT, Sangbae Kim in particular, they have a Cheetah robot, and it has a complicated control system that they don't know how to optimize. And so we've been helping them using these tools to essentially to get better gaits. So let me just show you a couple of examples. So here's a human-designed robotic cheetah gait. It's not very robust because it's quite difficult to run over random, even modest random terrain. And so it sort of like is kind of slow and kind of lopes along. And then if we run this thing overnight with Bayesian optimization, basically this is actually quite small. It's only 4 parameters, but 4 difficult to set parameters. Then we get a gait that's already essentially beats all of the human settings for these things. It takes a couple of hours to run one of these simulations, so this is something that takes kind of on the order of a day to compute, but already this is sort of like making a difference in this setup. So let me just wrap up. So basically, what this is about, broadly speaking, is trying to take humans out of the loop here and trying to come up with well-defined ways to go from a particular kind of machine learning generalization problem to a good solution without having to invoke the sort of black magic that often comes up in doing this kind of thing. And it turns out that at the end of the day, there's just sort of practical modeling decisions that you have to make at a low level to make it go. But we've also have a lot of new developments that I haven't talked about today, such as sharing information between different objectives, thinking about how to warp the parameter space to make things consistent, dealing with constraints, dealing with complicated discrete spaces like the DNA sequences I mentioned before, and kind of lots of new exciting applications. Thanks for listening. These are just a few of the collaborators involved in this. I mentioned code early on. There's a Python implementation of this that you can run on your cluster. You can go and grab it. And we're also trying to spin up a startup that's going to offer Bayesian optimization as a service through an API. So if you so you can either do this in a DIY way and spin it up and try it yourself, or hopefully you can plug in and run this with JSON over the web. Thanks a lot.
We do have time for a few questions. I'm sure there are questions. If not, I will be asking questions.
Great talk, by the way. Loved it. But I'm curious about how pervasive the assumptions of Gaussianity are throughout, because I imagine a lot of the analytics that falls out is because you can work through the algebra and obtain closed form expressions. And if for some reason there's a process where the underlying driving distributions are non-Gaussian, how easy would it be to extend this? And what is the risk of effectively sampling in the completely wrong places because the Gaussian assumptions are leading you in one direction, probably the variance is elsewhere because the distribution is totally different? And how can you kind of approach and mitigate that? And especially, how could you even know that may be happening, so that at least you say, well, even if this doesn't work, at least maybe you want to stop because this is going to mislead you?
Yeah, so great question. So there's 2 kinds of Gaussian assumptions that are going in here. One of them is the Gaussian process, which is technically Gaussian in the sense that we have with these Gaussian process sample paths. What that really corresponds to here is the assumption that the function is well behaved, where that means these things are like twice differentiable and continuous and so on. And the sort of the warping thing I mentioned at the end is about how we've been trying to deal with this, where essentially we're sort of transforming the space to allow it to be non-Gaussian, or at least non-sort of stationary. The second kind of Gaussianity here, and maybe this is the more troubling kind, is where the objective function is noisy and non-Gaussian. So I've shown everything as though it's noise-free, but of course real life is noisy and we can account for that. But if you're assuming a Gaussian likelihood and it's really non-Gaussian, then you could indeed get into trouble because maybe basically your residuals are sort of broken. And we don't deal with that right now. I think we could detect it using relatively off-the-shelf kind of model checking tools because it's just regression. But it's hard to know what the right sort of way to specify that a priori is. So if you know you're going to have those properties, so constraints have this issue where occasionally you try some location in your convolutional network and it core dumps, right? And so what do we give the regression then? And that's what the constraint story is about, where you have another GP, say, that is actually building a classifier of what the valid set of parameters is in addition to the objective function. And so that's one way we've been trying to deal with this kind of bad behavior, but frankly, it's an open question. Yep.
Sidon? Yeah. So optimization obviously has a long history. Can you elaborate a little bit on why is it that more traditional optimization methods have not been able to take the human out of the loop?
Okay, so I mean, absolutely, optimization is a big field with a long history, and even this particular kind of optimization that I've talked about today has in effect been around since the 50s. So I don't think that it's I think some of it is pure education. It's about just people being aware of the other field. I mean, machine learning is exciting and new, but it also has a tradition of being a little bit inward-facing, and so people maybe haven't made themselves as aware of good methods from the optimization literature as they could have. But also, I think this regime is quite challenging too. So this is a regime where things like you don't have gradients, so you can't use kind of an off-the-shelf LBFGS or whatever your favorite kind of nonlinear conjugate gradient tool is. It might be noisy, so even something like the simplex method, isn't likely to work. Things like evolutionary algorithms, people have applied to these, but those are really dumb, and so because they're random, right? So using more information and less noise is always better. And so I think it's a combination of kind of insights, but also I think the methods haven't quite existed. Frankly, part of the special sauce here is the fact that we're integrating out the hyperparameters using Markov chain Monte Carlo, and we do it in a way that doesn't require parameters because of some papers that I wrote with Ian Murray a couple of years ago that show how to do MCMC and Gaussian processes without any parameters. And so that removed a bunch of the difficulty from doing this kind of stuff, and that just didn't exist before.
Like that.
Yep.
You were discussing the need for an expert to run many of these models, and obviously you're talking about optimization, and if you looked at the variability of which expert you get as to how good the outcome is, and is the optimization really optimal? So you compare having one of your experts versus another expert running these and designing these models, designing these processes, and how much difference does it make? Do you know?
Well, I haven't done sort of interhuman comparisons. All I've done is compared the results of our algorithmic techniques to the humans who originally did the work.